Okay, we're going to do the last part, and we're going to discuss thermal expansion. So let me dismiss my image and proceed on with the lecture. If you ever drive on, I-10 going into town from about uh, about Woodlawn to um, uh, I think it's like the Santa Rosa exit. You're on an elevated section of I-10, and you can hear it on your tires. You'll hear this ka-thunk, 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 ka-thunk periodically, and it's when you are going over the expansion joints. You have to have the expansion joints because the road does expand. You don't sense that on the lower level. It's on the upper level. Or when you go from I-10 to I-35, there at uh, where that fine silver building all the way to till you get to uh, past Broadway. You on an elevated area, and you're going to get those same expansion joints, and you can hear as your tires go over the joints. So we're going to discuss thermal expansion. Thermal expansion, due to rise in temperature of a substance, molecules jiggle faster and move further apart. Most substances expand when heated and contract when cooled. Railroad tracks late on winter days expand and can buckle in hot summer. Warming metal lids on glass jars under hot water loosens the lid by more expansion of the lid than the jar. So if you have a stuck lid, run it under warm water. Um, okay, there's the railroad tracks, and you can see them buckling. Thermal expansion plays a role in construction and devices. Examples: use of reinforcing steel with the same rate of expansion as concrete, expansion joints on bridges. Gaps on concrete roadways and sidewalks allow for concrete expansion in the summer and contraction in the winter. Um, so the gaps, if we go up here to the beginning, you can see there's a little bit of gap uh, at these ends on either side. If it expands, it's going to close that gap. Um, okay, let's see. Thermal expansion. Different substances expand at different rates. When the temperature of a bimetallic strip of brass and iron is increased, greater expansion occurs for the brass strip, which bends to turn a pointer, to regulate a valve, or to close a switch. Bimetallic strips are used in heaters, oven thermometers, refrigerators, and electric toasters. I keep a small uh, circular thermometer in my uh, refrigerator, and it has a coil, a very thin coil that's of two different metals, and as it cools or warms, it contracts or expands accordingly and indicates the temperature on the gauge. Um, so they're showing here the brass uh, is when it's cold, it's contracting and it bends upward. At room temperature, they're the same. And when you heat the iron, well, uh, it looks like the brass is expanding quicker, and so it uh, bends um, bends it expands quicker and bends towards the iron. Okay. When stringing telephone lines between poles in the summer, it is advisable to allow the lines to sag, to be taut, to be close to the ground, to allow ample space for birds. Well, you're going to want to let them sag. The telephone lines are longer in a warmer summer, and shorter in a cold winter. Hence, they sag more on hot summer days and in winter. If the lines are not strung with enough sag in the summer, they might contract too much and snap during the winter, especially when carrying ice. So in the summer, you let them sag. Um, the increase in expansion are greater in the increases in expansion are greater in liquids than in solids. Example, overflow of gasoline from a car's tank on a hot day. You don't keep pumping and pumping until it's almost full. You leave a little gap, especially here in South Texas, where it can get up to over 100. Once it cuts off, just cap your gas tank and put up the pump. Gasoline underground is cool, but when placed in the car's trunk, it warms and expands. Okay, expansion of water. This is actually a little extra. They're taking the time to speak about water because water has some very unique properties that are very fortunate. When water becomes ice, it expands. It makes this little um, matrix here. The liquid water is just bouncing around, but when it freezes, it makes this nice little design expands and becomes less dense. That's why ice in your iced tea floats because it's less dense and it flows to the top. Ice has open structured crystals resulting from strong bonds at certain angles that increase its volume. This makes ice less dense than liquid water. We'll see that that's very fortunate for aquatic life. As temperature increases past 0 degrees, the remaining ice crystals collapse, decreasing the volume of the water. At the same time, increasing molecular motion expands the volume. The collapsing effect dominates the expansion until the temperatures reach 4 degrees. As temperature exceeds 4 degrees, contraction. Expansion dominates contraction because most of the ice crystals have melted and water expands. So above 4 degrees, water acts like any other material that typically expands as you heat it. And here's a little example. See, from 0 to 4, it actually contracts. It goes down in density. The volume changes for 1 gram sample of water. So let's look at the. I'll read it. It's in your book, but I'll read the captions. At position 1, the liquid water below 4 degrees is bloated with ice crystals. At 2, upon warming, the crystals collapse, resulting in a smaller volume for the liquid water. So it actually contracts. Above 4 degrees C, the liquid water expands as it is heated because of greater molecular motion. So from 4 degrees up, it acts like any other material and expands with rising temperature. Okay, thermal expansion of water. When water freezes to become solid ice, its volume increases tremendously, about 9%. As ice cools further, it contracts. The density of ice at any temperature is much lower than the density of liquid water. This explains why ice floats on liquid water. Now, this is I said this was very fortunate to aquatic life. If let's just say if this were not the case, when ice freezes, it becomes less dense and it floats. If that were not the case, as the surface water froze and sank to the bottom, well, eventually you'd freeze the whole pond or lake, and it would kill all the aquatic life on it. So it actually performs a protective barrier and saves the aquatic life underneath it. As water is cooled at the surface, it sinks until the temperature of the entire lake is 4 degrees Celsius. Only then can the surface water cool to 0 degrees without sinking. Once ice is formed, Temperatures lower than 4 degrees can extend down into the lake. Okay, and that saves all the aquatic life. When a sample of 0 degrees water is heated, it actually contracts. We saw that um, in this little 0 degrees is going to contract. So let's look at the answer. It contracts. When a sample of 0 degrees seawater is heated, it contracts. Water contracts as its temperature rises from 0 degrees to 4 degrees C. As the temperature increases beyond 4 degrees, water then expands. When a sample of water of 4 degrees water is cool, um, it it expands. Parts of the water will crystallize and occupy more space. And that's the end of the chapter. So let's uh, stop the share and end the lecture, and we'll see y'all